Welcome you all for this video about probability distributions. Probability theory is an important branch of mathematics. Generally, the word probability is used to denote the happening of a certain event and the likelihood of the occurrence of that event based on the past experiences. For example, by looking at the clear sky, one will say that there will not be a rain today. On the other hand, by looking at the cloudy sky or overcast sky, one will say that there will be a rain today. In the earlier sentence, we aim that there will not be a rain, and in the latter, we expect rain. On the other hand, a mathematician says that the probability of rain is 0 in the first case and the probability of rain is 1 in the second case. In between 0 and 1, there are fractions denoting the chance of event occurring. Similarly, if we consider another example, if a coin is tossed, the coin falls down. The coin has two sides, head and tail. On tossing a coin may fall down either with the head up or tail up. A coin on reaching the ground will not be stand on its edge, or rather we assume so the probability of the coin coming down is 1. The probability of head coming up is 50% and the tail coming up is 50%. In other words, we say that the probability of the head or the tail coming up is 1 by 2. Since head and tail share equal chances, the probability that will come down head or tail is unity. So this is about the basis of the probability. The theory of the probability is the base on which the law of statistical regularity and the law of inertia of large numbers are formed. It is based on the decision theory. It is very helpful to find the uncertainties of chances of success. So, next we see about the marginal and conditional distributions. So, marginal and conditional distributions are essential concepts in probability theory and statistics. They help us to find the relationship between the random variable and make predictions based on the partial information. The joint probability distribution is a probability distribution of two or more random variables. It describes the probability of each possible combination of values for the random variables. For example, if we consider a discrete case, then the joint distribution is defined as follows. Suppose we roll two dice x and y. The joint probability distribution of x and y is given by P of x comma y equal to 1 by 36. Here x varies from 1 to 6 and y varies from 1 to 6. So the probability of an event occurs is 1 by 36. Next we see about the marginal probability distribution. The marginal probability distribution of a random variable is the probability distribution of x alone, ignoring the other random variables. Suppose if we have the two random variables x and y, then we are going to concentrate on one distribution, that is one random variable, means we can define P of x equal to summation probability of x equal to x comma y equal to y over all y. So when we consider two dice, then the joint distribution of x and y of the two random variables is defined by P of x equal to 1 by 6, where x equal to 1, 2, etc. 6. Similarly, we can define the probability of y equal to small y equal to 1 by 6 for y equal to 1, 2, etc. 6. Next we see about the joint probability distribution of a two random variables. Suppose if x and y are the discrete random variables and f of x comma y is the value of their joint probability distribution at x comma y, then the function given by g of x equal to summation over y f of x comma y and h of y equal to summation over x f of x comma y are the marginal distributions of x and y respectively. So this is for the discrete case. Next we see the continuous case. Then f of x is defined by integral f of x comma y dy over all y. Similarly, f of y can be written as integral f of x comma y dx over all x. Next we see the conditional distribution. So before that we see conditional probability distribution. The conditional probability distribution of a random variable capital X given y equal to small y is the probability distribution of x when capital Y equal to small y. The conditional probability distribution is defined by p of x given y equal to p of x comma y divided by p of y equal to small y. So here we have the values x with the given value y. So we have the formula conditional probability distribution. So for this, consider the example. We roll a 2 dice and consider the x and y are the two random variables correspondingly. Then the conditional distribution of x given y equal to 6 is defined by probability of x equal to small x given y equal to 6, and which is 1 by 6, since we have only one possibility, 1 by 6 for x equal to 1, 2, etc. 6. Now let us consider one example related to the probability distribution. A balanced coin is tossed 4 times. List the elements of a sample space that are presumed to be equally likely. That means the coin being balanced and the corresponding values of x of a random variable x, the total number of hits. That means here we are going to consider the total number of hits occurred in the 4 tosses. So if h and t stand for head and tail, then the results are given in the following table. Elements of a sample space. Suppose if we are having 4 heads simultaneously 4 times after tossing, then we have x equal to 4 and the corresponding probability is 1 by 16. Suppose if we take x equal to 3, that means we have 3 heads and 1 tail. Then the possibilities are h h h t, h h t h, h t h h, t h h h. So we have the equal probability 1 by 16, 1 by 16, 1 by 16 and 1 by 16. Similarly, if we take x equal to 2, then h h t t, h t h t, then h t t h, t h h t, t h t h, t t h h. So we have the possibilities totally 6. So we have, when we take x equal to say x equal to 2, then we have 6 possibilities. Similarly, if we take x equal to 1, then we have the possibility h t t t, t h t t, t t h t, t t t h. So we have 4 possibility. Suppose if we don't get head, then there is only one possibility t t t t, like h h h. So the probability is 1 by 16, but x equal to 0. So we have taken the probabilities correspondingly in the table. So now if we write probability of x equal to 3, that is equal to 4 by 16. So x equal to 3 means we have the 4 possibilities. So 1 by 16 plus 1 by 16 plus 1 by 16 plus 1 by 16 gives 4 by 16. So this is the way of calculating the probability distributions when we have the real time example. Now let us consider another example, rolling of a 2 dice. So in the rolling of a 2 dice, we have the total number of the 2 dice. Suppose a dice means we have the sample space 1, 2, etc. 6. Similarly, if we take the second dice, then that also we have the sample space 1, 2, etc. 6. So if we roll a die, the minimum occurs is 1, 1. So 1 plus 1 is 2. So x value starts with 2 and ends with 6 plus 6, 12. So clearly we can see that x equal to 2 means there is only one possibility, which is 1 by 36. Suppose if we take x equal to 3, then we have the two possibility, that is 1, 2 and 2, 1. So 2 by 36. And if we take x equal to 4, then the possibilities are 1, 3, 3, 1, 2, 2. So the probability is 3 by 36. If we take x equal to 5, then 1, 4, 4, 1, 2, 3, 3, 2. So we have 4 by 36. Similarly, we can calculate the values when x equal to 6, 7, 8, 9, 10, 11 and 12. So in the table, in the second column, those values are given. So we can write the table like this way, but instead of writing or displaying the probabilities like this way, we can simply denote this table as f of x equal to 6 minus modulus of x minus 7 divided by 36 for x equal to 2, 3, etc. 12. So if we take this distribution function f of x, and if we substitute the values x equal to 2, etc. up to 12, then we will get the table again. So we, instead of writing all the possibilities in a table, we can write simply f of x equal to 6 minus modulus of x minus 7 divided by 36. So for example, if we put x equal to 2 in the equation f of x, we have f of 2 equal to 6 minus modulus of 2 minus 7 divided by 36, which gives 6 minus 5 by 36, which means 1 by 36. So which is the first value on the table, 1 by 36 when x equal to 2. So similarly, we can check for all the values in the table, you will get the same probability. So next, in the last two example, we have seen the discrete case. Now we see one continuous case. So see the problem. Find the distribution function of a random variable capital X of f of x equal to 3 e power minus 3t and use it to re-evaluate p of 0.5 less than or equal to capital X less than or equal to 1. Now consider the case for x greater than 0. So then we know the formula that f of x equal to integral minus infinity to plus x f of t dt. So here we are taking x greater than 0. So integral varies from 0 to x 3 e power minus 3t into dt. So after integrating this, we have 1 minus e power minus 3x. Since f of x equal to 0 when x less than or equal to 0, we have f of x equal to 0 for x less than or equal to 0 and 1 minus e power minus 3x for x greater than 0. Now we have to find p of 0.5 less than or equal to x less than or equal to 1. So for that we use the formula, that is f of a less than or equal to x less than or equal to b equal to f of b minus f of a. So by using that formula here, we have p of 0.5 less than or equal to capital X less than or equal to 1 equal to f of 1 minus f of 0.5. Here a is 0.5 and b is 1. So after substituting this x in the value f of x, we have finally that 0.173. So this is the way of calculating the distribution function of a random variable x when we consider the continuous case. So next, see the another example. Find the formula for the probability distribution of a total number of heads obtained in the 4 tosses of a balanced coin. Suppose when we consider the balanced coin tossing 4 times, then we have seen in the table, that is probability of x equal to 0 is 1 by 16, and probability of x equal to 1 is 4 by 16, and probability of x equal to 2 is 6 by 16, and so on. So by using these values, we can see that in the numerator term 1, 4, 6, 4, 1 are there. So which are the coefficients of 4C0, 4C1, 4C2, 4C3, 4C4? So we can find the probability distribution simply as f of x equal to 4cx divided by 16 for x equal to 0, 1, 2, 3, 4, etc. So when we substitute x equal to 0, then 4c0 divided by 16, which gives 1 by 16. Similarly, if we substitute x equal to 2, then 4c2 divided by 16, which gives the value 6 by 16. So we can calculate that probability distribution by simply writing f of x equal to 4cx divided by 16. Next we see the another example. Check whether the function given by f of x equal to x plus 2 divided by 25 for x equal to 1, 2, 3, 4, 5 can serve as the probability distribution of a discrete random variable. So here the distribution function is given and we have to check whether it is a distribution function or not. So for that we have the two conditions, that is, one thing is the function f of x, probability distribution function f of x must be always greater than or equal to 0. That is according to the postulate of 1. Then the second postulate is, or axiom is, the sum of all the values f of x values equal to 1. That is summation f of x equal to 1. So we will see that when we substitute x equal to 1, then 1 plus 2 divided by 25, and if we substitute x equal to 5, then 5 plus 2 divided by 25. So all the values are clearly positive, so the first axiom is satisfied. Next we see that the summation. So f of 1 plus f of 2 plus etc. f of 5 equal to, we can see that 3 plus 4 plus 5 plus 6 plus 7 equal to 25, that is equal to 1. So we have the second postulate also satisfied. So we can say that f of x can serve as a probability distribution function of the discrete random variable. Now we see the probability distribution functions applications. Probability distribution provide a powerful tool for modeling and analyzing complex phenomena in various fields. So let us see some examples in various fields. So first one is finance risk analysis. The normal and log normal are used to model stock prices, portfolio returns and risk assessments. In the insurance, Poisson exponential distributions are used to model claim frequencies and severities. And in the risk assessment, ensures the probability distributions to assess policyholder risk and set premiums. In engineering, the probability distributions are used to model component failures and system reliability. So it is used in reliability engineering. Next we see in the quality in control. The normal and binomial distributions are used to monitor and control manufacturing processes. In medicinal field, probability distributions of binomial and normal are used to analyze treatment efficiency and safety. And epidemiology, the distribution Poisson and negative binomial are used to model disease incident and prevalence. Next, in the environmental science, it is used in the climate modeling, that is, normal and non-normal are used to model climate variables, temperature and precipitation. And water resources, the distribution gamma and log normal are used to model water flow and quality. Next, in the quality control, the probability distributions, normal and binomial distributions are used to monitor and control the manufacturing process. Next, in the traffic and transportation, the traffic flow modeling, that is in the probability distribution, Poisson and normal are used to model traffic volume and speed. Finally, in the machine learning and AI probabilistic models, the Bayesian networks, Gaussian mixture models are used to model uncertainty and make predictions. So these are all the some of the real life examples or real life applications used in the probability theory. Thank you all.